All right. Welcome, everyone, to zkStudyClub. Today, we're very excited to welcome Alex Ozdemir, who's going to be talking to us about compiler infrastructure for SNARKs and taking programs and compiling them into SNARKs, SMT solvers, etc. And so he's presenting his joint work, which is up on the screen here, that he did with colleagues Fraser Brown and Riyad Wabi. And with that, Alex, thank you very much for coming and speaking to us today, and looking forward to your presentation. Over to you.
Yeah, thank you, Alex. So as was advertised, I'll be talking about some work that I recently did with Fraser and Riyad on what I would see as one of the greatest barriers to bringing SNARKs to new applications, and that is this problem of compilation, surprisingly. So up on the slides, I have a picture here, where on the left-hand side, someone has an idea, some idea that seems like something that could be proven in zero knowledge, that would be useful to prove in zero knowledge. And on the right-hand side, I have the logo from the ZK podcast, which represents a zero knowledge proof. And the question is like, what does somebody have to do to take their idea and turn it into an actual zero knowledge proof? And the challenge is that what you have to do right now is you have to go through some kind of arithmetization. You have to turn your idea into R1CS, which is a kind of arithmetic circuit format or some other arithmetic circuit. And so before you even get to the zero knowledge proof part, you have this compilation problem, which is turning your high level idea into arithmetic. And that compilation problem is what this talk is about. So I've kind of cut down on the number of slides in this talk, and my hope is that that will leave us space to take questions interactively. If there's anything at any point in time that's confusing, just ask me about it.
R1CS is not the only relevant arithmetization, but carry on.
Yes, totally true. I pick it here as an example, but I think actually one of the most exciting things about this work is that we don't believe that it needs to be specific to R1CS at all. And we've been exploring R1CS so far, but well, you'll see. Okay, so as sort of a motivating example, if the general idea isn't exciting enough, I want to pitch like one idea that you could imagine applying zero knowledge to, which is bug bounties. So the way that bug bounties work are that you have some kind of code that is very important. So here I have a snippet, a real macro from OpenSSL, or it used to be in OpenSSL. I'm sorry, was there a question?
No, I think someone just joined with a bit of background noise. No problem.
Got you. Yeah, so here I have a macro that used to be in OpenSSL, real code, but no longer there. And the way that bug bounty systems work is that you have some kind of code base owner, who I've represented by a genie in this picture. And they're interested in finding bugs in this code. So what they do is they offer a reward to anybody who turns in a bug. And the idea is that they're incentivizing people to report bugs instead of trying to exploit them. And so the idea that they're hoping is that a bug finder will come and they'll look for bugs. And if they find a bug, they'll send it over.
Alex, there is a information arbitrage there. So if you really find a 0 day, so I used to be an OpenSSL list a very long while back, dev list. So if you find a bug and if you don't really have a fix for it instantaneously, the window opens up. So I guess what scheme you're going to propose could be like super interesting.
Yeah. No, I think that this like handover is challenging, and it's good to ask about like what the incentives are. And so like in particular, like one question that the bug finder has as soon as they hand over these inputs that demonstrate the problem is, are they actually going to get paid? And this sounds like kind of like paranoid, like, oh no, these code-based owners, it's not like they're malicious, but oftentimes what a bug is somewhat open to debate. And there can be a lot of debate that ensues. And we say this from experience. Fraser has lots of experience filing bug bounties against browsers. That's what she does all the time. And it's not even necessarily that the code base owner is malicious, but just that they're being obtuse or disagreeable. And in the back of everyone's mind is once you hand over the inputs, the bug finder no longer has any leverage here. In some sense, the code base owner has already gotten what they wanted. And so you could imagine applying zero knowledge to this problem. And so just theoretically, what you would do is have the bug finder hand over a proof that they're aware of some vulnerability in this system. And now you can go into that negotiation phase on equal footing. So maybe the bug finder also hands over the bug to some kind of escrow, and then you can do a sort of a clean exchange. Or maybe we just have the code base owner pay first once they've verified there's a valid bug report, and then they get the actual inputs. This opens up the space, the design space. But it's not quite possible right now. And the reason, or it's not immediately possible at least, and the reason is that the same reason that it's hard to apply zero knowledge in general, zero knowledge applies to these arithmetic formats. It doesn't apply to your high-level programs in C. So if the definition of your bug is about some C macro, then essentially you need to be able to compile C to R1CS. And this is just one instance of the general problem, which is that we need compilers from high-level languages to R1CS. And I like the bug bounty example because it makes clear what two properties these compilers need to have. The first property is they need to be efficient and that they need to produce small output. This is important for zero knowledge because the cryptography, the speed of the provers and the memory usage of the provers depends on how big your R1CS circuit is or how big your other arithmetic circuit is. And also the compilers need to be accurate. And sometimes people ignore this, but it's extremely relevant to the bug case. And it's relevant to good design of systems in general, which is that if you want your proof about this arithmetic circuit format to mean anything, it needs to accurately reflect the intended semantics of the statement. So if I have some C program and I compile it to R1CS and I want the proof to mean something about the original C program, then the R1CS needs to accurately capture the semantics of C. So there are these two goals for building these compilers. One, the efficiency of the compiler, and two, the accuracy. And they're both important. And in different situations, they have different levels of importance. So since this is an important problem, people have been very busy working on it, including some people in this call, I believe. And so I have a diagram here. On the left-hand side, I have a whole bunch of languages and compilers that help you build SNARKs. If I forgot yours, I'm sorry. It is ignorance, not malice. Please let me know. But just to survey the space, we have a whole bunch of different kinds of things going on here. We have languages that are very low level, like CirC, that are almost like a hardware description language where you're like assembling a circuit. And then we have languages or compilers that purport to be very high level, like Pekin, which is an academic research project that attempts to compile C to R1CS. I'm also lying a little bit in that not all of the languages in here actually target R1CS. Some of them target other arithmetic formats. So like Cairo, for example, does. But at the highest level, all of these are languages that are being compiled to arithmetic circuits of some kind or other. And what I want to emphasize about these projects is one, that a lot of them are very good. Like they achieve efficiency or accuracy in some good way. Many of them involve a custom high-level language that was designed just for the compiler that compiles them. Finally, that there's a lot of duplicated work. And with a lot of duplicated work, there's a lot of spotty coverage. So, I have up here Pekin. Pekin allegedly compiles from C to R1CS. It doesn't really do that very accurately at all. It makes all kinds of assumptions that are not at all consistent with the C specification. And the reason is because they were really focusing on the efficiency side of things. And people have so much time and so much resources. And as my college professor would say, only so many beans of cleverness. And they can't afford to do everything well. Yeah. So people cut corners to achieve their specific goals, and this work ends up not just being duplicated, but sort of duplicated spottily. So one fun exercise that I do with these different languages is I get out their compilers and I hit all the sort of edge cases that I'm aware of being hard to compile, and usually each compiler covers about half of them. That's my typical experience. So again, not to throw shade, this is a hard problem, and people have been really heroically trying to take it on again and again. And so our observation was that even though there might be different high-level languages that you want to compile to arithmetic, At the highest level, these different languages are not so different. And what we have is really a more general compilation problem. So on the right-hand side, I have some arithmetic circuit. And on the left-hand side, let's just say for now that we're compiling C to this arithmetic circuit. If you think about the features, the important features of this compilation problem, they're as follows. The circuit format is defined by being state-free or having extremely managed state. So there's this idea of every value in the circuit has exactly one value. There's no notion of time. Things do not change. The circuit format is non-uniform. So what we mean by this is that it operates on a set size of input. So like high-level programs can operate on lists of any size. That's not the case for circuits. They're stamped out. They have static size. They operate on so many inputs, and that's it. If you want to operate on a different number of inputs, you need a bigger circuit. And then finally, the circuit format, because it's going to be used inside of a cryptographic proof system, is in some sense non-deterministic, in that there are these existential variables that can be proved or provided that you don't have to compute. You just have to check the validity of. And that's sort of like an interesting complexity theoretic feature of this computational model, that there's this prover that can give you values that you just check. You don't actually have to compute yourself. So that's what defines circuits. So high-level languages are quite different. High-level languages, first and foremost, are generally stateful. So they have things like mutable variables. They have these boxes that you can put values into, and then later on, you can put a different value into the same box. And intricately connected with this statefulness is the idea of control flow, that you can, in different situations, according to different inputs, take different actions. Not all code executes in every execution of the program. High-level languages are also uniform. They often, you can write down functions that operate on inputs of variable size, and you can use the same function for all these inputs, and the only difference is that it uses different quantities of resources. So if I write a function in Python that sums a list, it's going to take longer for a bigger list, but the same function will do the same job. So if you think about the compilation problem as going from some specific language like C to R1CS, then it seems very specific. But when you look at these lists of features, you realize that these features are actually shared with many other circuit formats on the right and many other high-level languages on the left. And if we start to just think about the circuit side, we see that similar circuits, or I have circuits here in quotes because they're not always called circuits in their respective community. But similar circuits are used in SMT solving and SMT-based verification. We would argue that SMT formula are circuits in the same sense. Circuits are also used for optimization. So if you want to use an integer linear programming solver or some other kind of real optimizer or a rational optimizer, then you give it a circuit format, something that's state-free, something that has non-deterministic semantics. And even if you want to do a multi-party computation, multi-party computation-based systems are built on either arithmetic circuits or Boolean circuits, depending on the underlying machinery. And those also are state-free and non-uniform. The non-determinism there is, it's easiest to say that there just isn't non-determinism. You can kind of slip a little in if you want. So since we observed that this problem is actually more general, our idea behind this project was to say, okay, rather than trying to continue to build one-off compilers from specific high-level languages to specific circuit formats, let's try to build a common infrastructure that supports these compilers in general. So what we envision is that CirC, which is our infrastructure, is sort of a railroad switching ground that's going to help you compile any high-level language to any kind of circuit format that you're interested in. And the hope is that by looking at this process in the abstract and by pulling as much of the compilation machinery as possible to a common level of abstraction, you're going to make extending this machinery to specific front-end languages and to specific back-end circuit formats far easier. And we've had some success with this, which I'll be telling you about over the course of the next 45 minutes or so. So in particular, what I'll be telling you guys about is our work building or extending CirC. First of all, building CirC itself. I'll tell you about the way the infrastructure is designed, but we've also gone through the work to extend CirC to a subset of C, to the complete zkStudyClub language, And we built backends for CirC for SMT solvers and also for cryptographic proof systems, specifically for R1CS, and we specifically connect it to Grot16, but the proof system itself is not so important.
Can I ask you a quick question about the name?
Yeah.
CirC, is it any reference to like the, what is it, Greek mythological witch?
Yeah, it's not.
Okay.
In fact, so Riyadh chose the name, and I think his idea was to be cutesy, not terrifying.
Okay.
It stands for Circuit Compiler.
Got it. And one other thing is Anish asked in the chat here, can you borrow anything from Llvm?
Oh, sorry, I can't see chat without advancing my slides.
No worries. That's why, no, you don't need to. Or myself or Alex will jump in and share that.
Cool. That's a great question. And that was our most important question when we started this project. And when we thought about it, we concluded that actually Llvm is almost wholly incompatible with what we're trying to do here. And let me say why. Llvm is a compiler infrastructure that's built around a particular computational model, which I call the RAM register model. You have some machine with lots of memory and lots of registers, less registers than memory, but still registers. And you can branch, and manipulating registers, changing their state is cheap. And so in some sense, Llvm is very built around memory and state changes. And those in our context are both very expensive. So Llvm sort of optimizes in the wrong direction. If you want to look at this, basically the complexity theoretic observation that we would make is any compiler infrastructure has a computational model that it is totally married to. And Llvm has attached itself to the RAM register model, and we're attaching ourselves to the circuit model.
So can I ask a follow-up question?
Yes, please.
So if you have a BNF kind of structure, will that be in the right direction and the opposite direction?
When you say BNF, what do you mean?
You have trees and then
yes. I think that's like more getting into our direction. Yeah, like if you have some kind of branching program.
Yeah.
Yeah, I think that's more getting into our direction.
Thank you.
Yeah, and also I want to say we didn't believe Llvm like as an infrastructure solved our problems, but like building a front end for Llvm is not totally out of the question. Yeah. We just think there would be some very serious performance challenges there.
The reason I asked is like they have built the whole pipeline, right? So I know I've talked to some other people who have been working on solvers, so I kind of know. But if you think about a compiler construction toolkit, Llvm gives us the best we can actually get at this moment in time. So effort-wise, once you build a compiler, then the tool chain is there, then everything else becomes handled. That's what I was thinking.
Yeah, for sure. Yeah. And certainly people who the use of SMT solvers inspires most of this work. In my other life, I'm an SMT solver developer, so I'm very familiar with that world. And we're drawing on that extremely. Like basically all of our algorithms are from the SMT compilation literature. Okay, so let's talk a little bit about how we build this common infrastructure now. So the core picture is this one. So on the front end of CirC, you're going to have modules that target specific high-level languages and are tasked with turning those languages into some kind of CirC IR, which is going to be a circuit IR, not like Llvm. And these different modules are probably going to draw on common libraries, but we can conceptualize them as different for now. Then in the middle, you're going to have some optimization machinery that's going to transform this circuit format, maybe try to make it smaller, maybe try to replace high-level constructs in the circuit format with simpler ones. And then on the back end, you're going to take the optimized circuit representation and turn it into a representation that some specific constraint processing system can handle. So in the zero knowledge case, you're going to be trying to turn this into R1CS or AIR or some other kind of arithmetic circuit format. And in the SMT case, you would want to turn this into an SMT formula. So just to give you an illustration, an animation of how this would work, you're going to start with some high-level program, and you're going to feed it into the right front end. The front end is going to produce a circuit format, so or like a circuit IR. That IR is going to go into the core of CirC. It's going to get optimized. You're going to run and rerun optimizations for those of you who know about how you design sort of multipass optimizing compilers. But after you've optimized to your heart's content, you're going to hand off this circuit representation to some backend. And typically what we're going to be interested in for the purposes of this talk is the proof system backend. But just for the sake of variety, we'll say this time you give it to the SMT backend, and it spits out an SMT formula, which you can then go and ask an SMT solver about. So you can say, hey, this circuit represents a violation of some property that must hold in a program. SMT solver, can you find me a violation? So what I'm going to do for the rest of the talk is go through the different layers. We'll start on the front ends. And the reason that the front ends are important is because in a real way, the kind of extensibility that you want most often is the extensibility to new target languages, to new high-level languages. And the way that CirC achieves that flexibility is by making it easy to build new front ends. And so in some sense, like this is the most important extensibility axis. So I guess I'll give you kind of like the results first. In order to figure out whether or not our idea of what would make it easy to build a new front end actually made it easy to build a new front end, we tried to build a new front end. And we built one for Socrates, which is a language that was designed to be efficiently compiled to R1CS. As far as we know, the project started in 2018. It might have started earlier, but not been public, unclear. And it's a pretty good piece of software. I like when I use their compiler, I enjoy using it. Yeah, and on the whole, it's a pretty well developed software project. So if you look through the code base and count the lines of code, excluding things like ASTs or whatever, there's like 28,000 of them. They're in Rust. A lot of that is moving the compilation process itself, as well as a number of optimizations, and they get really low level in their optimizations. They have some SHA-specific stuff that's looking for majority functions and looking for bitwise ITEs. It took some time to build this infrastructure. I guess the project's been going for 3 years now, and there are 36 contributors. And on the whole, I would say they produce pretty good output. It's rare that I feed something into the Socrates compiler, and I think they could have done like orders of magnitude better on that. So they generally produce pretty small R1CS for the language that they support. Although it's worth noting the Socrates language is somewhat restricted. There's no data-dependent control flow or stuff like that. Anyways, so we set out to build I guess another compiler for Socrates based on CirC, which amounted just to building a front end to CirC that handled Socrates. And we were able to do that, and we were able to do that quite easily. So ultimately, our front end is only 700 lines of code. It was built in 1 week by one person, me. And at the end of the day, it actually produces output that is on average better than what the Socrates compiler produces. Not always better, but on average better. So let me show you the plot for that. Here we have a diagram where we've taken various circuits from the Socrates standard library. Those are on the x-axis. And the y-axis is the constraint ratio. So it's the number of constraints that CirC produces when it compiles the circuits divided by the number of constraints that the Socrates reference compiler produces. When this number is small, that means CirC is producing less constraints, which is better for CirC. And the landscape is that in more situations, CirC does better. There's one benchmark where we do a little bit worse, which is the SHA-to-round function. And we can actually dig into this plot in detail now or later if you guys want, and we could talk about like what the compilers are doing differently and why they're getting different levels of efficiency. But what
the Pedersen one, is that the Bell-Hopwood-Pedersen that's used in zcash?
Yeah. I guess you're the right person to ask that question. Yeah. This is their implementation of that hash function. Yeah, so we chose a lot of hash functions that went into this plot, also some elliptic curve operations, and then also some sort of like bread and butter casting between fields and booleans and stuff like that. So yeah, to be clear, we're not saying that the Socrates compiler is garbage. Actually, I think it's extremely good. You should probably keep using it. But what we are saying is that if what you're setting out to do is compile some high-level languages to a constraint format, then maybe you should look into using our infrastructure because it's going to help you get extremely competitive performance extremely easily. without sacrificing accuracy. Okay, so that's kind of like the result on the front end side. Let's talk about how we do this. Let's talk about
before you move on from this slide. So how do these figures compare to, say, a hand optimized I1CS? No, not written using Socrates, just.
That's a good question, and I think it's going to depend. I don't think I can give like a single unifying answer to that question.
Well, yeah, it would depend on the benchmark.
Yeah. I think so it's a good question. When you think about the domain where you have a programmer who's really going to sit down there and tune, I think the most important thing that the compiler can do is offer sort of predictable performance profiles. Like you want people to be able to optimize in the high level language and actually feel like they're hitting the base of what they want. Like CirC is not imposing any abstractions that are inherently costly, so we're not worried about hitting some kind of optimization floor. Like imagine that you're optimizing Python. Eventually, you kind of hit this floor that you can't get through because of Python's computational model. We don't have any problems like that, of which I'm aware. But in terms of like the performance profile, like how predictable the optimizations are, that's a good question, and we didn't try to quantify that. I think that would be a good thing for us to look into. Yeah.
I guess you can always, I mean, like people do with conventional programs, they write parts of it in assembler. You can write parts of it in hand optimized I1CS or whatever.
Yeah, that's what I was about to say. It pretty much depends on the person who does the optimization assembly, especially the assembly bit, which I'm very familiar with. The other bit, I don't have enough data points. Dara knows better than I do. So there you go.
Carry on.
Will do. Okay, so yeah, what does it actually look like to write a front end? Like, what did we have to do to build this Socrates front end to CirC? Let's talk about that. So reminding you of the original picture, we're going to have these different front end modules, which are compiling different high level languages to some kind of intermediate representation, which represents the circuit. This is going to be like kind of like an SMT-like representation. It'll have a very rich set of types, but it's a circuit representation. There's no state, there's no control flow, none of that. And so really the task of these front-end modules is twofold. First of all, they have to embed their language semantics into a circuit format. And second of all, they have to scrub all of these things like state and like control flow and stuff like that. And so different languages have different semantics. So I guess each front-end module is going to have to define its own semantics. But the notion of state scrubbing, the notion of control flow scrubbing, those are a common thread. And the front-end libraries for CirC are designed to sort of handle those for you when you build a new front-end. How exactly does that work? What we imagine is that each front-end is written as an interpreter for the language that it is a front-end for, but state management is abstracted out and is handled by CirCIR, or sorry, is handled by CirC itself. So what this gives you is automatic handling of the challenging parts of variables like mutation, scoping, etc. It gives you automatic handling of data-dependent arrays. It's going to give you automatic handling of control flow. And the way that you're going to get that is whenever you're writing interpreter and you have to do something related to variables or related to memory or related to control flow, you're not going to do it yourself. You're going to say, okay, I'm going to delegate that to this state management module that's provided to me by the compiler. So to make that a little more concrete, I have a snippet of what part of the interpreter for some high-level language would look like. This is written in Haskell, so bear with me. I'll explain to the best of my ability. So the idea here is that we're interpreting a language called bool pair, which is pretty simple. It's got booleans, it's got pairs, and that's it. It's also you got like data-dependent control flow, assignment, etc. And here we have a snippet of what it would look like to evaluate a statement in this language. And we're looking at two cases. We're looking at assignment and we're looking at if statements. So assignment is the first case. Here we want to assign some expr to a var. We start by evaluating the expr, which is some other part of the interpreter. And then if you're writing an interpreter and you're doing an assignment, now you have to do the assignment. You want to store the value that you have in this variable. If you were in some intro PL class and you were writing an interpreter, you would like have a hash map where you map variables to their current values, and you would store the value in this hash map. And what you do looks a lot like that, but it has totally different semantics. So at the blue arrow here, I have a call to CirC's SSA assign, static single assignment assign function, with var and with the value. And so what you're doing is you're saying, CirC, I want you to associate this value with this variable. And you can imagine that CirC is just like maintaining a hash map for you, and that like that will work. Like you will be able to write something that looks like a correct interpreter for that model. But what's actually happening behind the scenes is CirC is producing a new chunk of circuit that manages the new state of this variable. And it's doing that in a way that's consistent with control flow. So let's talk about the if statement now and talk about control flow. So in the if case, you have three things. You've got the conditional that you're testing on, and then you've got some chunk of code, a statement that corresponds to the true case and a statement for the false case. And what you have to do is evaluate the conditional. And then you do this interesting pair of things. First of all, you use CirC's guarded function based on the condition that you just evaluated, which tells CirC, hey, I want to perform some further computation in an environment that's guarded by this condition being true. So that's the call to guarded. And then you use CirC's scoped function, which says, I want to enter a new lexical scope. And then inside that, you evaluate the true statement. And then right after that, you do the same thing for false. And you can imagine that like, oh, CirC's guarded is just kind of like a conditional, like it checks whether C is true. And if so, it runs the code that I gave it. But what's actually happening behind the scenes is that CirC is generating different chunks of circuit for the true case and for the false case. And it's sort of like state merging between them in a consistent way. So ultimately, this interface that you get is very much like writing an interpreter, or maybe like a type checker, because I guess when you hit a branch, you explore both directions. But the effect is that because you've been using CirC to do state management throughout, at the end of the day, you get a circuit. You don't get a type check result. You don't get a value. You get a circuit.
So things like the lifetimes of variables, will it automatically decide when a variable is no longer used? And I guess it doesn't matter because it's not as though you have to explicitly throw away the state. Yeah, so
that's actually
the
interesting.
optimizations that conventional compilers do are not really relevant here.
Yeah, we started this project thinking that we were doing something like Llvm, and just as time went on, we increasingly realized that's not true. We're doing something that's a lot more like an SMT solver. So we inherit most of our optimizations from the design of SMT solvers, actually.
I mean, the kind of caching and trade-offs in the Llvm thing, I don't think you can actually use it over here.
Yeah. Now I do want to say something about Daira's question, which is that this is the question of supporting high-level languages with sort of like complex constructor-destructor semantics is an interesting one.
Yeah.
That CirC is not helping you with right now. I don't think that means that it couldn't help you with it. I would like to think more about that.
Right. So if a language did have constraints on when things should be dropped, it would have to implement that itself.
Right now, yeah, it would have to implement that itself.
I guess it's not too bad.
Yeah, that being said, like if you're aware of such a language, like I would love to look into this more. Like perhaps there's some general infrastructure we can offer for that. I suspect there is.
I mean, Rust might be a good language to use as an example there.
Yeah. I'll file that away as something to look into. Okay, I think I might actually just want to skip this slide. Yeah. Okay, cool. So the next thing I want to talk about is the core of CirC. So I want to talk a little bit about the compilation algorithms that we use to do state management, and I'm going to talk a little bit about the optimizations that we apply on the resulting circuits. So that means that we're focusing here on the center of the compiler. And giving credit where it's due, to my knowledge, none of our compilation techniques are new. We're taking existing work and we're just lifting it to the right level of abstraction. If we accidentally came up with something new, that's very cool, but I don't think that certainly our intent was not to develop some new compiler infrastructure or new compiler ideas here, just to build an infrastructure that was at a sufficiently general level of abstraction that it could be reused. So I conceptualized most of the techniques that I'm going to tell you about as coming from the SMT-based verification world. Riyadh conceptualizes many of them as coming from the R1CS compilation world. And there's a lot of commonality and some differences. Okay, so let's talk about a list of challenges that we have to overcome and general approaches to overcoming them. So one immediate challenge is that in high-level languages, variables can mutate. Our infrastructure is responsible for managing that. And our approach, generally speaking, is to version all variables. So think about this as putting the program into a static single assignment form. If we start with code that says x equals y, and then say, okay, now we want x to be x times y, then these two different assignments are actually to two different versions of x. And I have that on the lower right-hand side. Another challenge is memory use. So generally, what do I mean by memory? I mean that we're accessing some kind of array, and we're accessing it at data-dependent locations. So you can imagine that here we have an array x, and we want to set location y to be some other value z. In the SMT world, the general way that you handle this is you use SMT arrays, which are designed to take care of this. And you imagine that what you're actually doing here is treating x as this abstract array. And when you assign to it, you're creating a new version of that array. So think of it as like updating a map. And the updated version at location y, you have z. There's actually a few like subways that you can handle this. There's often a debate. Do you make each high-level language array its own SMT array? Do you have one giant SMT array that represents the whole stack? How exactly do you want to handle that? Great questions. I'll talk about them a little bit more later. And you also might be thinking, okay, what if I'm compiling to R1CS? Even if something like SMT has arrays, R1CS does not. Just going to SMT arrays is not going to solve the problem. I'm going to kick the can on that too to a point where I talk about optimizations later on. We'll have a way to get rid of these SMT arrays in an R1CS friendly fashion.
So I'm not quite sure what the semantics of SMT arrays are. They're basically functional arrays.
Yep, exactly.
Oh, okay,
functional arrays.
So exactly what you would expect from that. Okay.
Yeah. So at first pass, we just need to turn all memory use into manipulating functional arrays. And if we're targeting some backend that doesn't support functional arrays, then we'll have to get rid of them in some fashion. I'll tell you guys about that in a little while. Another challenge is loops. There's lots of exciting techniques that you can use here on the SMT side. I don't think they've been explored as much on the R1CS side, but for this project, we just took a naive approach and we said we're going to unroll them. And if the loop is conditional, then we're going to unroll it with conditionals. So the next question is how do you handle conditionals? And the general approach is that you're going to guard all state mutations under a conditional context. So if I have some if statement, so at the top here, I say if y is equal to 0, then square x. Then when I create the new version of x, I'm going to emit an if then else, like a functional conditional expression, which either keeps the original value of x or produces a new one. And this conditional is guarded under the current context.
So going back to the loops for a second, I mean, that works if you have a static bound on the number of iterations. What if you don't?
Yeah, if you don't, then we can't help you right now.
Okay.
So we can guess.
Answer.
Yeah, I want to emphasize here that there's a lot of study into loops, especially on the SMT side, and we think that it would be interesting to look into this more. And we have some friends that are looking into it more as we speak, building on CirC. Yeah, but in some sense, in this work, I think we took the dumbest algorithm at every step of the way, and it's cool that the results were still pretty good despite doing that. Okay, so this is just a list of different techniques that we use to handle various high-level language constructs that are challenging to compile. After we've compiled into a circuit representation, it's time for optimization. Many of the optimizations that we do are basic ones, constant folding optimizations, where either you evaluate constant expressions or you evaluate you simplify operands that are applied to some constants. Operator flattening, looking for n-area operators and turning them into bigger ones. Substitution, if somewhere you say x equals y, then you can get rid of one of x or y. How you do that optimally is a hard problem, but doing it at all is pretty easy and is very useful. And then also people optimizations. So looking for common ways of expressing things that have better expressions. So here I have an example of something that turns up in hash functions where you have a sort of bitwise ITE expressed in terms of machine bitwise operations. So you can actually just turn that into like some kind of weird bitwise ITE, which might be more efficient. We won't go too much into these kinds of basic optimizations. You can imagine them as being stolen from an SMT solver or stolen from a compiler. They work the way you would expect. More interesting is how you handle things like arrays for backends that don't support arrays. So a common abstraction in various high-level languages that intend to target R1CS is that they only allow arrays to be accessed at constant indices. So for example, this actually isn't quite what Socrates does, but I think this is what Zinc does. And even if you're allowed to access arrays at data-dependent indices, oftentimes people don't. They just write some for loop that goes over the array. And so you want to be able to handle arrays that we say are accessed obliviously, that are accessed at only constant indices. And what you can do here is that you can replace the array with a sequence of distinct terms. Those terms are manipulated independently. You can think of this as being a very strong version of traditional scalar replacement optimization passes. And I have an example of this in action on the right-hand side. We have some array X that has two elements, and then you add its two values together and store them in the first location, and then you access that. So here, all of our indices are constant, and we can imagine creating X0 and X1 for the 0th and the first indices and manipulating them separately. So this is one optimization pass that we do. We look for arrays like this and we transform them. What about arrays that are not trivial in this fashion? Arrays that are actually accessed at data-dependent locations. To our knowledge, the best algorithms for this situation are sort of derived from routing-based memory checking. So the observation is this: if you've got some program, or in our case a circuit, that accesses an array at a number of locations, then you can imagine that what you actually have is a big list of array accesses, which are in some kind of program order. So here, the numbers 0 through 4 are the order in which this array is accessed in the program. And then there's a few variables associated with each access, whether or not that access is a load or a store, which address you're looking at, and which value either that you read from the array, or if you're doing a write, that you write to the array. It's pretty hard to check such a sequence of accesses for consistency, for read over write consistency. But if the array was in address order, then it would be pretty easy. You could just look at each pair of accesses and say, hey, if this is the same address, am I reading the last value? And if this is a new address, am I reading the default value? Like maybe that's 0, it depends on your language. And so the challenge is really just going from program order to address order, because once you're in address order, it's easy enough to check correct semantics. And so what you can do here is you can use various kinds of routing networks. We have an implementation based on Waxman routing networks, but you can imagine other things. Since you're in this prover verifier setting where the prover can provide things, it can do things like set the routing network switches for you. And so really all the network is doing is checking that these two lists are permutations of one another.
It's worth pointing out that some proof systems support that natively, just checking permutations.
Yeah, totally. So like in particular, like you can just like interpret both the sequences as polynomials and check for equality at a random location. Yeah.
Use a product argument, yeah.
Yep. So that if your proof system supports it natively is far better, and you should 1000% do that. But it does require you to be able to like sort of like insert verifier derived randomness into the circuit. But yeah, so in general, and the way we implement this is like you have the original order and the old order, and you stamp out some kind of permutation argument, and if you have a better one, great, plug that in there, and it'll be better. Okay, so to be clear, also, like, this is not our work or our idea. I have a list of citations on the bottom of the page. People have been doing this before, but this is how. But we express this algorithm at the level of this IR, which means it applies to any front end and any back end that we're using. So this is the end of talking about the middle part of CirC. At this point, we'll talk about the backends briefly. So we support two backends right now. One of them is SMT, specifically the Z3 SMT solver, which is kind of like crossing over to the wrong side of the street for me because I work on CPC4, which is a different solver. But we already had bindings for Z3, so that's what we targeted. Broadly speaking, our Z3 backend supports everything that we have in our IR. SMT solvers are very expressive. It's not that hard to support many things. The one thing we do not support is raw statements about finite fields. And then we also have a backend for R1CS, and it supports bit vectors, so machine fixed width integers. It supports Booleans, it supports finite field elements, and it supports some arrays via the kinds of transformations that I was just talking about. So one thing that we found that was very intriguing to us and validated the utility of general purpose infrastructure, not just general across input language, but also general across target, across backend, is the fact that some of the optimizations that I was just talking about seem to benefit both of these backends. Some of this is unsurprising. Constant folding is probably universally a good idea. And we find that is the case. So to demonstrate that, we define some hash function that's kind of like SHA-E, but not secure, pretty small. And it made a statement that said that the hash function evaluated at some input produced 0 as the final byte. And then we tried compiling this for varying sizes of inputs and with and without the constant folding pass enabled. And what we did is we said, okay, we're not just going to measure the performance of the R1CS backend or the performance of the SMT backend. We're going to measure both and see how both these backends perform under this optimization. And what we found is, I think, what you'd expect, which is that both SMT solvers and cryptographic proof systems appreciate you doing constant folding for them. In the case of the cryptographic proof system, between the blue points, which is where we have constant folding enabled, and the red points, which is where we don't, we have something like a 10-fold improvement. So this is huge. You should 100% do this. In the case of the SMT solver, the improvement is less, and the reason is that the SMT solver is going to do constant folding itself. So really, all you're doing here is saving it the work. So this is like simple enough, but it validated our intuition that there are at least some optimizations that benefit both backends. But we were curious whether or not there are more meaningful optimizations that also benefit both backends, and we found that there are. So another example is array elimination. So this is looking for arrays that are accessed at constant indices and replacing them with sequences of distinct values. To do that, we constructed a program that filled an array with non-deterministic values and then summed them. This is basically just 2 for loops where the indices of the for loops can be determined at compile time. And in this situation, we also found that both the backends appreciate this optimization. They appreciate it in extremely similar ways. The most sort of detailed common performance characteristic experiment that we did relates to array granularity. So I mentioned before that, broadly speaking, the way that you handle memory when compiling to a circuit is by treating memory as a sort of a functional array, and that you have a choice about how you do this, which is that you can try to represent each high-level language array with its own functional array, or you can try to put them all into the same bucket, sort of having a large stack array that every high-level language array is just an offset into. And these two different approaches have their own benefits and drawbacks. Generally speaking, if you take the stack approach, it's easier to capture language semantics accurately. But what we find is that the fine-grained approach performs much better, not just for SMT solvers, but also for compiling to R1CS. And in order to simulate this, it's not like we have some switch where we can switch to stack mode. Like we believed upfront that the fine-grained approach was going to be better, and so we only implemented that. But we can sort of simulate the stack-based approach by, at the source level, taking some program and rewriting it to merge all of the arrays. So we cooked up some program that used a whole bunch of arrays. In this case, each array represented a permutation over the index space of the array, and we just applied indexed one array after the other in order to apply this permutation. And then we made some statement like this permutation has a preimage for 0, which is of course true because it's a permutation. And on the SMT solver side, the solver is just trying to invert the permutation. And on the constraint system side, on the zero knowledge proof side, you're trying to prove knowledge of a preimage. And then what we varied was not just the size of the permutations, but also what fraction of them we had fused into a single array. And what we found is that not only does this increasing the size of the permutations degrade performance for both R1CS and for SMT, but also fusing degrades performance. So if you look at these plots, as you go from the left to the right, the x-axis that is, we're not increasing the memory footprint of the program. We're just fusing more of the arrays together. And we see that both the SMT solver and the R1CS backend perform worse as you fuse more of the arrays together. And the reason this is a problem for the SMT solver is it's starting to reason about more accesses to the same array, which is challenging for it. This is a problem for R1CS because your routing networks are getting bigger and bigger.
Yeah, that is actually something where having a native permutation argument makes a difference, because the cost of the native permutation argument is just linear in the number of elements.
Yeah, you're totally right. So if the way that you handle these kinds of arrays is sort of strictly linear asymptotically, then you wouldn't expect it to matter a lot how big your arrays are. And actually, to be frank, because the stack approach is much easier to model semantically, I think this is a strong argument for supporting permutation arguments in your proof system. It gives you a better path forward when it comes to modeling memory, which is a pretty pervasive abstraction.
Although my intuition would have been that the smaller arrays are better anyway, but I wouldn't have had a clear idea of why.
Yeah. Yeah. So anyways, just the trade-off of array representation from granular from coarse to fine is something that people have looked at a lot in the SMT world, and largely we're confirming that the intuitions that they have also apply here. Which is very cool, and it bolsters this argument that there's a lot of common optimization machinery that you can write. Okay, so enough of the graphs and details. One interesting thing that you can also do when you support multiple backends is that you can do sort of interesting crossovers where you try to use one backend in service of the other backend. So I'll tell you about two such applications that we looked at. One of them is using an SMT solver to help you compile to R1CS. So to use the SMT solver sort of in the service of optimization. And this goes to the question earlier about handling loops. What if you don't know how many times the loop is going to run? Naively, what you'd have to do is guess or get some input from the programmer. And one example that might be challenging is the example I have up on the screen. So this is a program that's supposed to be computing the base 2 integer logarithm of a 32-bit number, and it's doing that with a loop that iterates until some value is 0. And naively, it's not clear how many times this loop is going to run. And that's a very important question, because if you guess a number that's too big, then you're producing a circuit that's too big, and that hurts you on the performance side. If you guess a number that's too small, then your compiler is not going to be complete. You're going to be preventing valid executions of the program because you're going to guess a number that's too small, and you're probably going to emit some constraint that says the loop actually stops at that point. And that's going to invalidate certain program executions. So it would be good to have a precise answer to the upper bound of the number of times that this loop iterates. And with an SMT solver, you can actually get a handle on that. So we wrote, I think it was literally 10 lines of code that what it does is that when you're using the C front end to the system, while you're unrolling a loop, at each stage, you take the circuit you've assembled so far. And even though your ultimate goal is to turn it into R1CS, you take what you have and you give it to an SMT solver. And you say, hey, is the current path of the program still feasible? And if the SMT solver says yes, then you keep unrolling. But if the SMT solver says no, then you know that you've reached an upper bound of the number of iterations and you can immediately stop. So to be clear, we're asking the SMT solver to solve a pretty challenging problem here, and this isn't going to work all the time. But what we found to be exciting is the fact that having common infrastructure made this so easy to implement. We already had a backend for SMT. It was just a matter of saying, hey, SMT solver, take what we currently have and tell us something about it.
So this example, suppose that you had a very large integer. Would it still be feasible with the SMT solver? Could it, or is it only practical for small values?
Yeah, for loops of this simple structure, I think the SMT solver is going to like chew through it no matter how big the integer is.
Okay.
Like, I mean, we're going to get into the details a little bit here, but so the way SMT solvers handle bit vectors or machine integers is they turn them into SAT, by and large. Not universally true, but that's the dominant approach. And when the operation that you're doing inside the loop is this kind of shift that has an extremely efficient SAT representation. And basically like the solver is going to end up ignoring almost the entirety of your state space. And it's just going to follow the most significant bit. I think where you're going to run into more trouble is where the control flow inside the loop gets more complicated.
Yeah. Yeah, because it could easily end up being exponential in that case.
Yeah, for sure. So using SMT solvers to say things about your program, rich area of research, lots of cool things that you could try to bring to bear here. We just did the simplest cut, and our observation is that with common infrastructure, whatever you're trying to do with the SMT solver, it's extremely easy.
This is very cool.
Yeah. Okay, but we're not done yet. So I have one more crossover application. This goes back to what I opened the talk with, doing a proof of bug. And I mentioned before that this is challenging because you need to be extremely accurate in order to capture most bugs. Your compiler really needs to capture the input language semantics. But we were designing this infrastructure to not just support compiling to R1CS, but also support compiling to SMT. And accuracy is always the paramount concern when compiling to SMT. And so that means that we sort of get it for free on the R1CS side. So we sort of rigged up this interesting little workflow where we take some input program. So I have it here. This is, again, the same macro from OpenSSL. It's supposed to be computing C equals C plus 2AB. It doesn't quite do that. The carry handling is a little bit broken. I have a backup slide if you want me to like give you a data flow diagram and explain how this macro is broken. So what do? We say, okay, we're going to take this macro and some assertion about its behavior. We're going to use the C front end to compile them into our intermediate representation. Then we're going to take that intermediate representation. We're going to feed it into an SMT solver. We're going to get back from the SMT solver a violation of the property. And then we're going to take that violation, we're going to lower it to R1CS. And we're going to write a zero knowledge proof that we're aware of this violation. So this is like sort of an interesting little demo to do. If the bug is so easy that a generic SMT solver can find it, then writing a zero knowledge proof is kind of a waste of time. But if you replace step 3, find violation with solver, with some sort of custom analysis, then what you have here is in some sense a demonstration of the zero knowledge proof of bug system. So we thought this was kind of fun to do, and what we and the point that we wanted to make here is that the only reason this works is because we're achieving sort of an accuracy bar that's high enough for SMT, and that enables the zero knowledge proof to actually mean something about the program that it underlies. Okay, so I guess we're at the end of the road here. I've been telling you guys about CirC. This is, broadly speaking, a compilation infrastructure, not for programs, not for assembly, but for circuits. Our observation is that different circuits and different high-level languages can share the same compilation infrastructure, and that when you build common infrastructure, it makes it easy to support new languages. It enables any new language that you support to benefit immediately from optimizations that have been defined in the compiler infrastructure itself. And it also enables these interesting crossover applications where you start to use the different backends which have different purposes in service of one another. This is work that we're just getting started on. There's lots of directions we want to take it. I can give you the details if you want, but maybe I'll stop for now.
Awesome. Thanks, Alex. We got, well, I guess we're going to open up to questions now. Anish, I think, Anish, you had a question you just posted in the chat, so okay, feel free.
All right. Alex, rather stupid question. I was kind of extending this. It's like, normally one of the problems we have in this blockchain space is like you make a bunch of cryptoeconomic assumptions, you create a contract, and the protocol is broken, not as a bug. The bug that you're referring to is like a bug, you have an assertion, you understand it at a first level. So imagine you have a multiple levels. I was just thinking that's what a cryptoeconomic attack would look like, right? So how hard would that be to actually have like multiple levels of assertions?
I see. Yeah. So you're saying that like in some sense, there's some behavior from the circuit which is broken, but it's not broken because of the circuit itself. It's broken because of some interaction with the circuit in the outside world. Yeah. I think that this is a challenging case for us, and the reason I think it's challenging is that essentially, what you need to do is you need to encode that higher level stuff in a format that the compiler can understand. And you could imagine doing that, like saying, I have a hard time coming up with an example, but making whatever kind of incentive statement that you want. The challenge is that for these kinds of proofs, you need to perform the setup for the zero knowledge proof. And at setup time, you need to agree about what a bug looks like. And my instinct for these kinds of multi-layer attacks is that they're often very creative. Like you don't necessarily know a priori what the incentive situation is going to be, which defines the bug. And so I think that would be a challenge, sort of like not necessarily it's not even a compiler challenge, right? That's just like a sort of a human challenge. That using a zero knowledge proof requires you to agree up front about what a bug is.
I mean, I guess that you could use existing tools that are designed to prove the security of cryptographic protocols, for example, and then where CirC is helping here is knowing that the representation that you feed to that system corresponds to your actual circuit.
Yes, that is a good point. Yeah, so if you want to do some kind of analysis in like some kind of interactive proof assistant where like you're saying something,
I see.
something like that. Yeah.
Okay. Thanks, Dara. Thanks, Alex.
So
it's just a stupid thought.
No, it's a
good
thought.
At all.
So what interests me actually is using the SMT solver to prove the correctness of optimizations. So these could be optimizations that are too hard for a compiler to do automatically. Say they're based on the mathematical statements about the elliptic curves you're using or whatever. So they're too hard for the compiler to do automatically, but they may also be difficult to prove by hand. So that's what I'm most interested in. Have you explored that area much?
We've started to think about it. In fact, actually, broadly speaking, the kind of thing that you describe has been on my mind for years now. And the challenge is that you need to get well, it depends on what optimizations you're thinking about. But probably, I think that the interesting thing to do here would be to analyze optimizations that involve the arithmetic format itself. So either mapping bit vectors into arithmetic or arithmetic itself, whatever. And in order to get the SMT solver to tell you things about those optimizations, you need the SMT solver to be able to reason about field arithmetic.
Yeah.
And you can approximate that right now. Yeah, you can approximate that right now with integers, like for prime fields or something with modulus. But like the modulus machinery in SMT solvers is pretty garbage. Actually, that's not quite right. It's over-engineered because it's designed to support any modulus, like even a symbolic modulus, whereas in our context, the modulus is fixed. And so I think it's extremely interesting to try to develop better support for finite field arithmetic in SMT solvers. And I think that would enable the kind of analysis that you're talking about, and also lots of other interesting analyses as well.
So in SMT terms, this is just a theory, right?
Yes, this is just a theory. We want a theory of finite fields. Yeah.
I don't know whether there's been any work on that.
I've looked, and I've talked to people like Clark and all the folks at SRI, and we're not aware of any.
I mean, there are plenty of optimizations that don't depend on finite fields. There's one that's used in zkStudyClub, for example, when you're doing a range check for a fixed range that you know in advance, and you use the bit pattern of the size of the range, and that's exactly the kind of thing that an SMT solver would just eat up.
Yes, you're right there. Yeah. So for those kinds of optimizations, you could definitely get an SMT solver involved. And if you express those optimizations in our machinery, then it would be really easy to, when you like stamp out the optimization in one situation, you can check just that instance. You could also ask the compiler to do it sort of symbolically and check the optimization in general.
That particular one was about a couple of days to prove correctness. So I would really be very happy if something could do that automatically, or even with less help.
Yeah.
Awesome. Alex, this is super interesting. My question is more on, I think, getting back to the applications and really the crossovers, and you've got these dotted lines here to some other areas that, some folks on the call obviously recognize MPC, because MPC is what we do for a lot of setup ceremonies in zero knowledge. But also, I personally am interested in ILP and just optimization in general. And so I'm curious about, so you've kind of given a couple flavors of how this could look, where SMT, the SMT solver can be combined, because it's a unified infrastructure with some other stuff on the back end. What other promising directions for combinations do you see? Maybe including, that you could bring in ILP or MPC.
Great question. And yeah, one that's been on our mind from the beginning. I'll give you two. One of them that's like pretty well formed, and one of them that is just starting to take form. The well-formed thing would be to use optimization machinery in the service of some kind of compiler optimization pass. So to have at some stage in the compiler some representation of what you're compiling, and then ask an ILP solver, hey, if I want to like try to write this as some alternative system of equations, what's the lowest cost way to do that? So I think this is kind of obvious. You might imagine using the optimization solvers in service of compiler optimization. Another interesting opportunity is based on the observation that if you open up many MPC systems, they have inside of them, for purposes of malicious security or other purposes, the use of zero knowledge proofs. So like you can imagine that like during an MPC execution, there are phases where the protocol says, do a zero knowledge proof. And often that's treated as a black box. But if you're using a compiler infrastructure like this to actually build the MPC circuit, maybe you want to open that box up and actually like maybe add some more zero knowledge proofs of your own. So maybe at a certain phase, what has to happen is you have to come up with some value that needs to be legitimately computed. And traditionally, you sort of black box ship that to a zero knowledge proof, but we might actually be able to like open that up and try to optimize the zero knowledge proof and the MPC together. But so these are just two combinations that we see. I don't think we've spent as much time thinking about this as we would like, and I would love to hear of any other ideas that somebody has.
Yeah, no, this is really cool work, and I mean, to me, it just makes clear the connection between sort of these different fields that I hadn't appreciated as much before, and I know very little about compilers certainly, but yeah, cool.
Yeah. I think the story here is that it is fruitful to complain to Fraser when I'm having trouble building some kind of R1CS instance, or fruitful for her to complain to me when like SMT isn't doing what she wants. Eventually, we realized our complaints were basically about the same thing.
So you said you gave some statistics for how long it took you to build the Socrates front end. How long does it take to build a back end?
That's really
let's say for a different arithmetization.
Yeah. I think it depends on sort of like how far your particular circuit format is from the IR that we have.
Right. I mean, I guess you can treat more general formats. They have an R1CS special case. So
yeah,
you could start with the R1CS solver and then try to generalize it and make it more efficient.
Yeah, so supporting like some kind of like bounded fan-in arithmetic circuit, for example, like that you would use for MPC perhaps, or maybe you would use for I think the Planck description uses a bounded fan-in arithmetic circuit.
Planck is actually quite similar to Air in many ways.
Got you. But yeah, using one of these, I don't think that this would be the hardest thing to support. In fact, I think in many ways what you would do is you would take the R1CS backend and you would sort of like split it into 2 layers or something. The first layer would sort of arithmetize and the second layer would flatten. But we haven't looked into doing it yet. I think we have some plans to go down this path for MPC, but we haven't done it yet.
And how much work would you say was involved in writing the SMT backend or the R1CS backend?
Yeah.
I mean, I know that that's going to be much more than writing a new one because you've already got those examples.
Yeah, I can actually talk about this pretty concretely because we originally wrote this in Haskell, and I think once it became clear that it was a good idea and that people might want to use it, we've decided to rebuild it in Rust, which was something that we think people are more comfortable building on. And so we've been doing that. I did the Rust thing maybe like 2 days ago, and it took me like, I don't know, 3 evenings of work to do the R1CS backend in Rust. And then
wow, I'm impressed.
The SMT, to be fair, like I already knew everything I had to do because we had done it before, right? But
yeah, I know. But that puts a bound on what the complexity of it must be, which gives me an idea.
Yeah, and then the SMT backends are like super easy, right? Because like our IR has so much. In fact, for a long time we conceptualized our IR as just like extended SMT, where we've like thrown in finite fields and we've thrown in some other stuff that we wanted. So that mapping is very direct. Like I don't know, as fast as you can type, probably.
Cool, thank you.
Yeah.
Any other questions from the group here? Okay, I have one. I guess I'll pile on. So a lot of this work looks like you're using zkStudyClub, and obviously there's been several new, which you referenced, kind of languages that people have created to compile or to write high level logic that compiles to R1CS. I guess in a little more detail, do you think is there any interest from you or the other authors, or do you think there's promise in exploring looking at those as the front and replacing zkStudyClub with those in the front end? And what do you expect you might discover there if you did that?
We are extremely interested in using this infrastructure to compile new high-level languages. So like in some sense, like we built this as an infrastructure for people who are building new DSLs that intend to target zero knowledge proofs. So if you or people at your firm or whatever are thinking of some new language that you want to target some kind of arithmetic circuit, please come talk to us. We suspect this is useful for that task. We found that to be the case for zkStudyClub, and we would be like, I would love to have a conversation with anyone who's interested in doing that.
Got it. Yeah.
I'm incredibly interested. We should set up a conversation with Zcash people.
Yeah, yeah.
People.
If you have my email already, then you can use that. If you don't, I guess I can. My email is aozdemir @cs.stanford.edu.
Yeah,
I know some people. I'll pass it on.
Yeah. So actually, I should say in disclosure that this is like research software. I don't think that we're quite production ready yet, but like what we got so far seems really useful for this purpose.
Yeah, great. I guess my question a little bit deeper though is, zkStudyClub I think is somewhat more limited than some of the newer approaches. And so I guess so I think you benchmarked some of the, the improvements that you could get by using, this infrastructure. How would you expect that to compare with some of these other languages that have maybe fewer limitations than zkStudyClub?
Great question. Yeah, like zkStudyClub is like super limited, no data dependent control flow. I'm not even sure that they support data dependent array indexing, although I'd have to check. When we were designing the system, I told you guys about our comparisons against zkStudyClub, but most of our comparisons were actually against Pekin, which is a compiler from C to R1CS. And Pekin, while it's not nearly as nice as zkStudyClub, I would not recommend you use it. In fact, even building it is a pain in the butt. It supports all kinds of fancy things, and we compare very favorably to Pekin as well. So we're able to handle more complex program constructs. We're able to handle them well. And actually, for what it's worth, like our Socrates front end supports these as well, just because like the compiler natively does. So like in our Socrates, you can branch on data dependent values, and you can access arrays at data dependent locations. So you get the higher level stuff as well.
Cool.
Nice.
I guess alibi here for anybody. Final questions or anything they'd like to ask or say to Alex before we conclude here?
Thanks, Alex.
Yeah, no, thanks for being a great audience. It's been my pleasure to give this talk.
Thank you. This was awesome.
Yeah, thank you very much, Alex. As you can tell, we all really enjoyed this, and I maybe am speaking for myself, but likely I'm speaking for everyone, that I think this is a really cool direction to explore. This is different than many of the other talks that we, kind of see in this group and papers we review, and very excited about your future work on this subject. Hopefully we can welcome you back again at some point.
Maybe even for a more proof system-y thing.
Totally. Cool.
Awesome. All right.
Okay, I'll stop screen share.